The second fundamental theorem of calculus, which is really the same fundamental theorem of calculus, just looked at a different way, is that if g of x is equal to the definite integral from a to x of f of t dt, meaning g is some accumulation function, we'll talk about what that means in a minute, its derivative, g prime of x, is f of x, which is the integrand evaluated at the upper limit of integration. I know there's a lot of words to that sentence, but in the end it ends up being a pretty simple idea that if some function is the definite integral of another function, the derivative of the accumulation function is the integrand. G prime of x is f of x. Let's look at a couple of reasons why this is the case. Number one, let's start with a very mechanical reason. So here's an accumulation function. Again, we'll talk more about that word in a minute. K of x is the definite integral from negative 2 to x of cosine of t dt. Well, we can find k prime of x by rewriting k of x using the fundamental theorem. Because k of x is a definite integral that we actually know how to integrate, let's integrate it. The definite integral from negative 2 to x of cosine of t dt would be the antiderivative of the cosine of t, evaluated from negative 2 to x, which is the sine of x minus the sine of negative 2. That's k of x. And so k prime of x would just be the derivative of sine of x minus sine of negative 2, which is cosine of x. And then the derivative of the second term, the derivative of the sine of negative 2, is just 0, because the sine of negative 2 is a constant. So k prime of x is cosine of x. But notice that that's this, if you were to just take the upper limit of integration and plug it in. So because of the fundamental theorem of calculus, which states that the definite integral of a function is its antiderivative, sort of, that means that the derivative of that definite integral, the derivative of an antiderivative, is back where you started. So that's the idea of the second fundamental theorem of calculus. Another way to understand it is to think more about what it means to be an accumulation function. So we will naturally turn to Desmos for help. Here is an example of an accumulation function. The dotted line here is the square root of x. And then what I'm looking at here, the definite integral from 0 to a is my input, my independent variable. I'm going to control that with this. The definite integral from 0 to a is of f of t dt, that's my function. So right now, when a is 2, the definite integral is 1.8856 or so. Well, as I move my upper limit of integration up, the reason this is called an accumulation function is I'm raising the upper limit of integration, which means I'm just talking about more area. I'm accumulating more area. In other words, remember, the definite integral is an accumulated product. I'm just accumulating more area. And the input, the upper limit of integration, is telling me how far to go. What I want you to notice is what I have down here, these next two lines, two different things that are the same. The derivative in respect to a of my accumulation function, remember a is taking the place of x here, because that's how Desmos needs to work, and f of a, so just evaluating this integrand at whatever that number is, well, those are always going to be the same thing. And that's the main point. No matter what I make my a, the derivative of my accumulation function is the same thing as just f of a. And it makes total sense why this would be the case if I think about graphically what dg actually means on the graph. If g is the name of my accumulation function, then this whole thing here, this accumulated area, is g of x, which means that this extra little bit right here, the next little bit of area that I would accumulate, is dg. This red thing here, this red rectangle, is dg. Well, it's a rectangle. We can figure out what dg is. It's the product of its length times its width. Well, this width down here is dx. So dg equals something times dx. Well, what is this height over here? That is simply the height of the function at whatever x value I'm talking about. Remember, the x value is the upper limit of integration. So wherever I'm stopping that integral, the height at that moment is f of x. So dg, that red rectangle, is equal to f of x, the height of the red rectangle, times dx, the tiny little width of the red rectangle. Well, if I bring the dx over, I can write that as dg dx equals f of x. And dg dx is, of course, another way of saying g prime of x. So this is just another way of thinking about the second fundamental theorem in a way that makes sense. Some ways that we'll use this. Well, first of all, here's some multiple choice problems. Whenever you're looking at an accumulation function, and it's not like there's going to be a big red flashing sign that says, hey, this is an accumulation function, but you should be able to recognize the definite integral with the variable as the upper limit of integration. The first thing you need to identify, and say this right away, it's not always going to be the first thing you need to use, but say it right away, is that the derivative of that function is the integrand evaluated at the upper limit. G prime of x is f of x. So this question asks me which of the following values is greatest, and gives me a bunch of values of g of x. Well, the one that's greatest, we know this from earlier in the year, a function is maximized when it stops increasing and starts decreasing. And we know that that means its horizontal tangent, g prime, would have to be 0. So if we can identify the place where g prime is 0 and g prime is going from being positive to negative, I shouldn't say g prime of x, by the way, I should say g prime of a, because it's some constant. And g prime goes from being positive to negative, because g has to go from increasing to decreasing. Well, looking at my graph of f, remember, g prime of x is f of x. So g prime of x goes from positive to negative when f of x goes from positive to negative, which happens right here. G prime of x, which is f of x, goes from positive to negative at x equals 1. So g of x has a max. It's really a relative max. We can talk about why it's the overall max later in the year. Has a relative max at x equals 1. Look at one of these other ones. We'll just look at number 7. So here again, similar idea. It's a graph of f, and it tells us that this graph has horizontal tangents at x equals 2 and x equals 5, which means f prime of 2 is 0 and f prime of 5 is 0. Let g be the function. G of x is the accumulation function of f, so the definite integral from 0 to x of f of t dt, which means, again, the first thing you're going to say when you see that is that g prime of x is equal to f of x. So for what values of x does g have a point of inflection? This is something we've covered a little bit. We'll talk about more later in the year, but point of inflection means that on G means G double prime of X changes sign, either goes from positive to negative or vice versa. Well, since G prime of X is f of X, that means G double prime of X is the same thing as f prime of X I can spell sign. And we know that f prime of X is 0, and so it changes and goes from being positive to negative, or negative to positive, at the two places where there's a relative min or max on f, which we know from what the problem told us, that's at x equals 2 and x equals 5. One last thing to show you, a little extension of the fundamental theorem. You do have to be careful, like always, about the chain rule. So we have the second fundamental theorem, which is that if we have an accumulation function, its derivative is the integrand evaluated at the upper limit of integration. Well, if that upper limit of integration is its own function, we would think of that as the inside function. Which means chain rule, you have to remember the chain rule. So when we take f prime of x, it's still the integrand, t cubed minus 5 to the 4th, evaluated at the upper limit of integration. So that's plugging that in for t. X squared cubed minus 5 to the 4th. Chain rule times the derivative of the inside function. So because of that chain rule, we're going to multiply by 2x. And so my final answer for f prime of x would be 2x times, I'm not going to FOIL all this out, but I will turn x squared cubed into x to the 6th. And that would be a good way to leave it. The next one's similar idea, slightly more complicated. P prime of x would be the integrand evaluated at the upper limit of integration. So tan of x squared. I'm going to put the x squared in brackets there. If that, just to make it clear what it means, because it looks a little bit vague there, if it would have meant tan of x squared, it would have to have been written as tan squared of x. So that's not what it said, so that's not what it means. Either way, tan of x squared squared, that's my t squared. But because of the chain rule, we need to multiply by the derivative of that tan of x squared, which is a little bit of a lot, secant squared of x squared. But chain rule again, there's more inside times the derivative of the inside, times 2x. So this is, I'll rewrite it with the 2x first. 2x times the tan squared of x squared times the secant squared of x squared. And tangent times secant doesn't get simplified because that's sine over cosine times 1 over cosine. There's nothing helpful we can do there, so I will leave it like this. And that is your answer.